Okay, so let's go ahead and get started. So what I wanted today was continue our discussion of spin 1/2 particles equation, spin 1/2 particles in classical field theory. In particular, what I want to do is talk in a little bit more detail about the Dirac equation, which is the classical equation of motion obeyed by spin 1/2 particles, and discuss the solutions of the classical equation before next class proceeding to quantize the theory somewhat along the lines of our quantization of the free scalar field theory that we went through about a week and a half ago. So let me just remind you of where we left off last class. Okay. So our goal is to construct Lorentz invariant theories, so theories consistent with the symmetries of special relativity, describing particles that have spin. So a scalar, typically denoted phi, is also referred to as a spin 0 particle. It has no spin. Examples of scalars that might occur include, for example, the Higgs field in the Standard Model as a scalar, the inflaton, which is the field that putatively drove the expansion of the universe at very early times. In condensed matter physics, for example, the field describing a Cooper pair in superconductivity is a scalar field. The phonons, which are the excitations of some lattice, the propagating wave excitations of a lattice, are described by a scalar field. We've also met a vector field, which has 4 components, which describes a particle that is said to have spin 1. The electromagnetic field, of course, is a vector field. In the context of condensed matter systems, the dynamics of an electric field might be modified in some ways. So, for example, in a superconductor, the electromagnetic field acquires a mass. That essentially is the theory of superconductivity. All of the force-carrying particles of the Standard Model are vector fields, the carriers of the weak nuclear force, the strong nuclear force, and so forth. And today we're going to be discussing the theory of spinors, which describes spin 1/2 particles. Okay. And the spinors, so spin 1/2 particles include, for example, all of the elementary particles that make up matter: electrons, quarks, and so forth. Whereas the vector fields describe those which transmit forces, electromagnetic forces, nuclear forces, and so forth. And of course, as we mentioned earlier in this class, one could also construct other fields with other values of spin. For example, there is a spin 2 field, the graviton, which is also a force carrier responsible for the force of gravity. And there may well be other sorts of field with other different kinds of spin out there. So just to remind you of what we discussed last time, a spinor, psi, is a 4-component complex field. So if you wanted to, you could think of psi as, so it's some function of where you are in space-time. You could think of it as a column vector with 4 components, or you could write it in an abstract index notation as an object with a spinor index A that runs from 1 to 4. But usually in this class, in order to keep notation as compact as possible, we're just going to not write out the spinor index explicitly, not write things as a column vector explicitly, if we can help it, and just refer to the 4 components as a spinor field psi. The Dirac equation was constructed in terms of the gamma matrices, denoted gamma mu, which are 4x4 matrices obeying the Clifford algebra, which says that their anti-commutator is proportional to either 1 or minus 1. And we wrote out explicitly what the gamma matrices are. So they're 4 by 4 matrices, and we can write them in 2 by 2 form, where each of those entries in the 2 by 2 matrix is itself a 2 by 2 matrix. And they're given quite simply in terms of the Pauli matrices. And although we didn't do it last class, I believe on the problem set that you're going to do for Friday, you'll verify explicitly that these obey the Clifford algebra. It's really not very hard. It's a straightforward consequence of the algebra of the Pauli matrices. So very often in this class, we may want to write this in a slightly more compact notation. So I'll just introduce a little bit of notation here. So remember that the Pauli matrices, there are 3 of them, and they act like a vector under rotations. You know, sigma 1, sigma 2, sigma 3 describe spin in the x, y, and z directions. So the I index on the Pauli matrices, sigma I, acts like a 3-dimensional vector under rotations. So it makes sense to define a quantity that I'll call sigma mu, which behaves a bit like a 4 vector under Lorentz transformations. And in fact, this is really just notation more than anything else. We can define another 4 vector, sigma bar mu. So these are 4 vectors, each component of which is a 2 by 2 matrix. But as usual, I'm going to suppress those spinor indices. And then with that notation, the gamma mu's can be written a little bit more compactly as that set of 2 by 2 off-diagonal matrices. So these are the gamma matrices, and my claim last time, which you'll verify on a problem set, is that the commutators obey the algebra, that is to say, the commutation relations of the Lorentz transformations. So that just as the fact that the Pauli matrices obey the same algebra as rotations in 3 dimensions means that you can describe particles with spin as things that are acted on by these Pauli matrices. Similarly, we can because these S mu nus obey the algebra of the Lorentz group, you can construct Lorentz invariant theories describing particles with spin by using these S mu nus as operators acting on spinors. In particular, in the same sense that, for example, sigma 3 in quantum mechanics is the operator that would measure the amount of spin in the z direction. S, say, 0, 1 here is an operator that would measure something corresponding to a boost in the x direction. So more specifically, under some Lorentz transformation, say where our coordinates get rotated by some Lorentz matrix, some 4 by 4 Lorentz matrix, as we saw last time, this Lorentz matrix can be regarded as the exponential of some infinitesimal generator J mu nu, which generates an infinitesimal Lorentz transformation, times some parameters omega mu nu. So in the case where you just wanted to describe a rotation, then J12, for example, would be a rotation around the z-axis, and omega 12 would be the angle with which you rotate. So this would be the usual expression for a rotation generator is e to the I theta times J3 for a rotation around the z-axis. But if you wanted to do a boost, you would use J01, and you would set omega 01 to be non-zero, for example. under such a Lorentz transformation, the spinors are not invariant, but rather transform by the action of a matrix, which we called lambda to the 1/2. So in addition to the point x transforming in the usual way, the 4-component spinor gets multiplied by a 4x4 matrix that we call lambda to the 1/2. And lambda to the 1/2 is just the exponential of the generator S mu nu of Lorentz transformations acting on this spinor index. So this is sort of a review of what we did last time. So there were a bunch of sort of calculational details that we relegated to exercises, many of which you'll be doing for Friday. There's nothing particularly fancy going on here, but I realize it's a lot of new notation. So maybe this is a good time for me to stop and see if there are any questions. Is all of this relatively clear? I mean, we're going to spend this class and indeed a lot of, this semester kind of unpacking and understanding some of these details. But hopefully is at least the basic structure clear? Good. Yes, question. Good.
Can you repeat what you said about omega mu nu and j mu nu and what they correspond?
Yes. So for example, when you think of these things as differential operators, J12 is, x dy minus y dx, right? Which is the generator of rotations about the z-axis. And omega 12 would be, you could call that some angle, say theta sub z. Then if you wrote down lambda, which is e to the I, say, omega 12, j12, what is that? That generates a rotation by an angle theta about the z-axis. Indeed, if you just imagine how that acts on, say, some function of x and y, what does it do? It takes x to cosine theta x plus sine theta y, and it takes y to minus sine theta x plus cosine theta y, which is just the usual way that a rotation about the z-axis acts on the x and y coordinates. If that's not obvious, then I encourage you to work it out for yourselves, either on your own time or when you're doing the problem set that's due on Friday. And then the point being that if you have some spinor and you want to ask what happens to a spinor when you do a rotation, well, what happens to a scalar when you do a rotation is that the value of the scalar field phi at some point, xy, will just get moved to the value at the points, x prime, y prime, where the x primes and y prime are related by a rotation to the initial x and y coordinates. And that's all that happens. But if you have a spinor, in addition, that spinor will get acted on by a 2x2 matrix, or sorry, a 4x4 matrix. And what is that matrix? It's e to the I theta times S12. And this should hopefully all be reasonably familiar to you from quantum mechanics. So in non-relativistic quantum mechanics, a 2-component spinor is acted on by the rotation matrix e to the I theta, say sigma 3, if you wanted to describe a rotation by an angle theta about the z-axis. In particular, if you had a spin 1/2 particle and it was in some state, described by a vector in the 2-dimensional Hilbert space of a spin 1/2 particle, and you want to do a rotation by an angle theta about the z-axis. So let's say you have some experiment where you have some spin 1/2 particle and you put it in a magnetic field or something like that to make it rotate. Then you would act on it with this matrix, e to the I theta sigma 3. So that's quantum mechanics, and what I'm doing here now is, promoting that to a theory with Lorentz invariance. Questions?
Okay, so the lambda matrices are 4x4.
Lambda are 4x4 matrices.
So I don't quite see that from the
Okay.
exponential form, because it looks like you're just going to be summing over all of the
Good.
matrices.
Yes. Good. So remember that I'm suppressing the spinor indices here. Okay. So
Well,
Can't-
you've been acting on a 4 vector.
yeah. So lambda, okay, lambda to the 1/2 does not act on a 4 vector, it acts on a spinor index.
Yeah, but
So-
I don't mean necessarily lambda 1/2, just lambda or lambda 1/2.
Okay, yeah, I'm being a little schematic here. Okay, so lambda is, lambda that I've written here is very different from the lambda that I've written here, which is why I put a 1/2 under them. Lambda that I've written here is the exponential of a differential operator that acts on your coordinate axes. And so, for example, it takes the coordinate x mu to lambda mu nu x nu. Lambda that I've written down here is the thing that acts on a spinor. Okay. So this is a 4x4 matrix. Lambda to the 1/2 is a 4x4 matrix because these gammas are 4x4 matrices, so their commutators are 4x4 matrices. So that S here is a 4x4 matrix. And when you exponentiate a 4x4 matrix, what do you mean? You mean 1 plus the matrix plus 1/2 matrix squared plus 1/6 matrix cubed and so on and so forth. So that's another 4x4 matrix. Okay.
Yeah.
And that's the thing that acts on the spinor indices. But this lambda that I'm writing here, you know, I'm using a somewhat abstract notation where I've written it as the exponential of a differential operator. If you wanted to, you could write it as the 4x4 matrix lambda mu nu, the one that explicitly does the rotation. Okay. In particular, so in this case, you would write it as lambda mu nu is the matrix which has entries, you know, 1, 0, 0, 0, 0, 0 here. Then you would have what? A cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1. Okay. That would be the explicit representation of it as a 4x4 matrix. So I'm sort of using, in my head, two different ways of thinking. There's two different ways of thinking about the J mu nus. You can either think about them as differential operators, or you could think about them as infinitesimal 4x4 matrices. And in particular, you know, J mu nu is the infinitesimal 4x4 matrix whose elements are, you know, so for example, in that way of thinking about it, J12 is the 4x4 matrix whose entries are something like 1 and minus 1. So this is how J12 acts on 4 vectors, right? Whereas the differential operator that I've written here describes how rotation acts on functions. Is that clear? I mean, in the same way that in when you describe rotations, you could either describe the algebra of rotation matrices by writing down the 3 matrices that act on a vector, or you could talk about the generator of rotations x d by dy minus y d by dx. There's really just two different notations for the same
I guess
thing.
I'm just a little confused on how to go from the differential form of J12 to the matrix form.
Okay, so the first problem on the problem set that you will do this week describes precisely how to will force you to work out precisely how to do that. So maybe just as a preview, let's just take J12 to be x d by dy minus y d by dx. Okay. And let's look at this matrix lambda, which is e to the I theta J12. Okay. And let's act on it. Let's act on the vector xyz. Okay. So what does it take that to? So lambda on the vector xyz. What is it? Well, should we put a t up there so it's a 4 vector? Sure. Let's put a t there so it's a 4 vector. What is it? Well, it's 0, minus 1, minus x, minus, so d by dx, so minus y x 0, right? Otherwise known as 0, 0, 0, 0, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 0 times t, x, y, z, up to some sign that I always get wrong. Okay, so maybe I got the sign. So there's some I in here. Okay, right. So, yeah. Good. Is that clear?
Yeah, that's-
Okay, so hopefully, so that is what you will do on the first problem on the problem set. So if it wasn't already clear, hopefully that makes it clear exactly the relationship of these, the generators as differential operators to the generators as matrices. Good. Any questions? Yes.
Just to be sure, so J mu nu is we can think of it as a 4x4 matrix?
Yes. So you can think, so let's just be very, very clear. J mu nu, there are 16 of them, okay? It's really anti-symmetric, okay? So there's really 6 of them because it's you think of it as an anti-symmetric 4x4 matrix. And then you can think of it as a 4x4 matrix of differential operators or a 4x4 matrix of 4x4 matrices,
Yeah,
right?
I see where the 16 comes from, because I only see J mu nu.
Well, the 16 was just, you know, when I counted J mu nu, J mu and nu can both take one of 4 values. So there's 16 possible J mu nus. But it's anti-symmetric, and if you think about how many degrees of freedom are there in an anti-symmetric n by n matrix, well, there's n minus 1 times n minus 2 over 2, unless I'm wrong by a factor. But in a 4x4 matrix, there are 6 degrees of freedom. Yeah, you can count that out for yourself if that's not clear. Yes, question. Oh, sorry, yeah.
My question was, can we say that omega mu nu is also a 4x4 matrix?
Absolutely. Omega mu nu is a 4x4 matrix. It is an anti-symmetric 4x4 matrix whose entries are the 3 rotation and the 3 boost parameters describing an arbitrary Lorentz transformation. Right? So if you wanted to write it out explicitly, you know, it's an anti-symmetric matrix, so it has zeros along the diagonal. And then it's the 0, 1, you know, what would we call that? We would call that beta x, beta y, and beta z. And then you might call this, let's call it, so omega 1, 2 would be theta 3, or theta z, I guess you would call it, theta y, and theta x. Okay. And then all of the entries down here, because it's anti-symmetric, are just the minuses of the ones up above. Right. Is that, yeah, good. Good questions? Yes.
So, J mu nu and S mu nu are 2 different representations of the Lorentz.
Absolutely correct. Yes.
They have the same dimension.
Yes. Yes. So that's right. So there's no, right, good question. So J mu nu and as 4x4 matrices and S mu nu are 2 different representations of the Lorentz group that have the same dimension but are different. Okay. So what do they, and that means that they act on very different spaces. So what do the J mu nus as 4x4 matrices act on? They act on 4 vectors, which are 4-component objects that, you know, transform by multiplication by the usual Lorentz matrix. The S mu nus are a 4-dimensional representation that act on a 4-component object that has nothing to do with 4 vectors. It's a spinor. Okay. And so, you know, it's an accident of the fact that we're in 4 dimensions that the spinor representation and the vector representation happen to have the same dimension. Good question, yes. In the language, in the formal language of representation theory, we could give 2 different names to those representations. The name that you would give to the 4-vector representation is 2, 2. And the name that we would give to this Dirac spinor representation is 1, 2 plus 2, 1. Okay? So the fact that they have the same dimension is the fact that 2 times 2 is 2 plus 2. Right? Sometimes that happens. Yes? Question?
Now we have considered only spinor and vector representation.
Yes.
Do you have tensor representation?
Yes.
And again, like the lambda will be e to the I omega, some representation of the...
Absolutely. And tensors, so the representations for integer spin are kind of easy to construct. So for a graviton, what is a, you know, what is a graviton? A graviton would be a 2-index object that under a Lorentz transformation would transform like lambda mu alpha, lambda nu beta, h alpha beta. For those of you who've studied general relativity, you could recognize this as the transformation of the metric under a coordinate transformation. Okay. So, you know, and so for example, so that is the definition of what a spin 2 field is. It's something that transforms in this way. if we were very ambitious, we could talk in this course about spin 3/2 particles, okay, of which there are conjectured to be many, but observed to be none. Which would transform under some fancier representation of the Lorentz group and stuff like that. There's a whole zoology of these kinds of things. It's been classified. You can all look it up, but it's not something we're going to talk about in this class. Good. Yeah, please ask more questions. I want to make sure this is important, and it's good to make it clear. So I'm sort of taking my time for that reason because there's nothing particularly fancy, but it is a lot of new language. It is really a completely straightforward generalization of what you did in non-relativistic quantum mechanics, but in teaching this class I've discovered that nobody really understands it when they learn it in non-relativistic quantum mechanics. Sorry, many people don't understand it. I'm sure you are all the special ones who did. Good. Any other questions? Good. Okay. So, what is the point of introducing all of this stuff? Well, the idea, and this is a fact, I don't remember if I proved this to you last time or I stated it as something that you'll do on a problem set, but the fact is that the gamma matrices, so these are 4x4 matrices, have the very special property that if you conjugate them by one of these spinor matrices lambda to the 1/2 that describe the action, say, of a rotation on a spinor, then that just looks like the action of the Lorentz group on a vector index. So what does that mean? That means that under a Lorentz transformation, gamma transforms as a vector. What do I mean by that? I mean exactly this equation right here. Okay. Lambda mu nu, that 4x4 matrix, described how a vector transformed under a Lorentz transformation. And we can see that we can now take the mu index of the gamma matrices seriously as a vector index. And we can use it to construct Lorentz invariant quantities. And the most important use of that is in constructing the Dirac equation. In particular, what this means is that you can contract the gamma index with d by d x mu, okay, which also transformed like a vector. That's the chain rule of calculus, really, to make a quantity that is a scalar, gamma mu d mu. And then you can construct a good equation using this differential operator. And this equation is known as the Dirac equation. So here, just for fun, we've introduced a parameter m here, which, okay, no surprise, that's going to be related to the mass of the particles that are described by the solutions of the Dirac equation. And there's a factor of I here, which I'll comment on in a minute. So that I is important. There's a reason why I put it there. And in a few minutes, hopefully it'll become clear why that's there. So just to recapitulate, this is a first-order differential equation for a set of 4 complex quantities, psi, which are the components of a spinor field. And it turns out there are many different kinds of spinors. So later on in this lecture, we'll meet something called the Weyl spinor. Also, I don't know how much we'll talk about it. There are spinors called Majorana spinors. This spinor here, psi, is referred to as a Dirac spinor. We'll almost exclusively talk about Dirac spinors in this class. Good. And this is the classical equation of motion of a spin 1/2 particle. So it's useful to ask, how is this equation that we've written down related to the sorts of equations that we're more familiar with, such as the Klein-Gordon equation for a scalar field or Maxwell's equation for a gauge field? So in order to understand that, and also to get some practice manipulating the Dirac equation, let's just try the following. Okay. So this is the sort of trick that you'll get used to in this class. So this is the Dirac equation. Okay. So that guy is equal to 0. So let's act on this with another 4x4 matrix. In particular, let me act on this with the exact same thing, except with a minus sign put in front of that gamma mu d by d x mu. So what am I doing? Well, I've just acted on 0 with this fancy differential operator, so you'll still get 0. And let's now multiply this out. Okay. So this is the form of, sure. Do you want me to use different indices? Fine. Good idea. Let's use different indices so that we don't get confused. We'll call that gamma nu, del mu. So this is of the form, something plus something times something minus something, which is the form of something squared plus something squared, right? You know what I mean? So this is m squared, or let me write it as gamma nu mu d by dx nu d by dx mu plus m squared. I guess I factored out an overall minus sign, plus m squared. Oh no, I didn't factor out a minus sign. Acting on psi, okay. Because you have some cross terms, but the cross terms cancel. And we can stare at this guy here. And the first thing that you should notice is that by the equality of mixed partial derivatives, d by dx nu, d by dx mu is the same as d by dx mu, d by dx nu. Okay. So we could rewrite that. That means that we only care about the symmetric combination of gamma nu and gamma mu. So you could rewrite that as 1/2 gamma mu plus gamma nu gamma mu d by dx mu d by dx nu plus m squared. And what is this quantity here? Well, the Clifford algebra, that is to say the defining property of the gamma matrices, says that that is the metric. So what is this? This is grad squared plus m squared acting on psi has to be equal to 0. Otherwise known as the Klein-Gordon equation. In particular, one of the things to notice is that this operator here involves no gamma matrices. So it doesn't mix the different components of the spinor psi. So each component of psi will obey the Klein-Gordon equation. Indeed, the Klein-Gordon equation is sort of probably the most fundamental Lorentz invariant equation that is obeyed by a scalar. So we've discovered a scalar field will obey it. The Maxwell field, I believe, I don't know if you demonstrated this, but there's a particular choice of what's called gauge symmetry in Maxwell's equation, where you can show that the electric and magnetic potentials also obey the Klein-Gordon equation in that gauge. And we see here now that the components of a spinor also obey the Klein-Gordon equation. Indeed, it's probably worth mentioning at this point that this equation is responsible for a quite different interpretation of the Klein-Gordon equation. In particular, of the Dirac equation. The Dirac equation was initially postulated by Dirac as essentially a quantum wave equation which is sort of the square root of the Schrodinger equation. in the following sense. So we've seen here that if you take the Dirac equation and you square it, you'll get the Klein-Gordon equation. Remember, the initial way that we derived the Klein-Gordon equation is that we guessed it as the generalization of the Schrodinger equation for a quantum wave function to a particle to a theory of special relativity. And indeed, we started this class with the observation that the Schrodinger equation, so if you tried to write down the Schrodinger equation for a quantum mechanical wave function describing the Hamiltonian of special relativity rather than of Newtonian physics, we found that this was problematic and in part it was problematic because it treated space and time in different manners. In particular, if you just look at this Schrodinger equation that we wrote down here, one of the things that immediately pops out at you is the fact that the left-hand side of this equation is linear in time derivatives, whereas the right-hand side of this equation involves this complicated square root. So clearly this equation, although we tried to write down a version of the Schrodinger equation that was consistent with special relativity, treats time and space very differently. And so the way that Dirac initially guessed the Dirac equation is that he looked at this version of the Schrodinger equation and he said, well, let's imagine that psi is not a single component wave function, but rather lives in some Hilbert space which has the property that this operator, or let me write it this way, this operator that we're taking the square root of, grad squared plus m squared, is actually a perfect square. So in particular, we're going to search for matrices alpha and beta, we'll need 3 alphas and 1 beta, such that the operator that you're taking a square of is actually a perfect square. Then one can just take the square root in the Schrodinger equation and you get I d by dt of psi is I alpha dotted into the gradient plus beta m times psi. And now you can easily convince yourselves that if alpha and beta are just numbers, then it's impossible for this equation up here to be true. Instead, you need to take alpha and beta to be matrices. And in order to determine what those matrices are, let me rewrite this equation in a somewhat more suggestive form. Let me just rewrite it as I gamma mu d by dx nu minus m acting on psi is equal to 0, where gamma is now a set of 4 matrices, the first of which is beta inverse and the second of which, the other 3 of which are beta inverse times alpha. So indeed, you can see that the gamma matrices that we constructed are nothing more or nothing less than the matrices that you would need if you wanted to take the square root of this relativistic Schrodinger operator to write down a version of Schrodinger's equation which is sort of treats space and time in a completely democratic way. So the reason why the Klein-Gordon operator didn't make sense as a wave. The Klein-Gordon equation didn't make sense as a wave equation for a quantum mechanical wave function was that it was second order in time derivatives, so we couldn't find a conserved probability. But if you can construct an equation that's first order in time derivatives, then that is something that might be a sensible sensible wave equation for a quantum wave function. And indeed, what Dirac showed is that you just need to find a set of four matrices that obey this particular property right there, and then you can find the square root of the Schrodinger equation. And indeed, it's a straightforward exercise to show that the Clifford algebra that we wrote down above is just precisely the algebra that alpha and beta have to satisfy in order for this equation here to be true. So in this interpretation, Dirac viewed the Dirac equation as an equation for a quantum wave function. It's important to remember that in this class, the Dirac equation is the wave equation for a classical field, like the electromagnetic field. But you can still get a lot of intuition about spinors and quantum field theory if you think about the Dirac equation as a quantum wave function as well. Right? Indeed, when we discuss the classical solution of the Dirac equation, which we'll be doing later on this class or next class, we'll probably come back to that interpretation. For those of you who have seen the Dirac equation in your quantum mechanics classes, it was almost certainly in this context. Any questions? Is that familiar to those of you who've seen the Dirac equation before? You probably didn't see it phrased in terms of the gamma matrices. That's just an efficient repackaging of the same equation. Good. Questions? Okay. So the scalar field theory and the electromagnetic field theory both have equations of motion which follow from the minimization of an action. And so it's natural to ask whether the Dirac equation also follows from the minimization of an action. In particular, does it follow from some sort of Lagrangian formulation of the theory of spin 1/2 particles? So, in order to answer this question, remember that in order to have a Lorentz invariant theory, we need to require that the Lagrange density L is a scalar. That is to say, it's just one number per point in space-time. It doesn't transform in any fancy way under Lorentz transformations. And from this, if you have the Euler-Lagrange equations that you derive by varying a scalar Lagrangian with respect to a field variation, those Euler-Lagrange equations are guaranteed to be transformed nicely under Lorentz transformations. So in order to construct the Lagrangian for spin 1/2 particles, then, we need to find some way of constructing scalars out of spinors. And so this is when we're going to start getting some practice with manipulating these spinors. So remember that psi is a complex four-component object, which you could view as a column vector. And psi dagger, therefore, is going to be a four-component row vector. So the natural scalar that one might try and form is psi dagger psi. But unfortunately, psi dagger psi is not a scalar. Why is that? Well, let's ask how this guy transforms under a Lorentz transformation. Well, you trans psi picks up a factor of that matrix lambda to the 1/2. And so psi dagger psi picks up the action of this matrix lambda to the 1/2 dagger times lambda to the 1/2, where lambda to the 1/2 is e to the I omega mu nu S mu nu, where S mu nu is that set of 4x4 matrices that we wrote down above. The problem is that this matrix lambda to the 1/2 is not a unitary matrix. That is to say, lambda dagger is not lambda inverse. Okay. So the unitary matrix is one whose inverse is equal to its Hermitian conjugate, and lambda to the 1/2 is not a unitary matrix. So, in particular, let's just see that explicitly. So, what were these matrices S mu nu? Well, Sij, where I and j run from 1 up to 3, is easy to compute. So, remember that these gamma ij's, so this is the anti-commutator of gamma I with gamma j. Gamma I and gamma j were just defined in terms of the Pauli matrices sigma I and sigma j. So it's a sort of very straightforward calculation to compute this. And you find that Sij is 1/2 epsilon ijk sigma k, where sigma k sits on the diagonal. Now, this is, of course, exactly what you would expect, because I told you that psi was a spin 1/2 particle. And remember that, so for example, S12 is something like sigma 3 along the diagonal. What is sigma 3? Sigma 3 is the thing that for spin 1/2 particles in non-relativistic quantum mechanics describe the generator of a rotation about the z-axis. So you can see that for our 4-component spinners, the upper 2 components and the lower 2 components are behaving just like a spin 1/2 particle in non-relativistic quantum mechanics. So this is just some sort of straightforward generalization of the generators of rotation in non-relativistic quantum mechanics to quantum mechanics. And we see here that everything kind of gets doubled. The 2-component spinners of quantum mechanics become 4-component spinners. Okay. Well, Sij is Hermitian because the Pauli matrices are Hermitian. So what does that mean? That means that, say, e to the I Sij dagger is e to the minus I Sij. So if you just have a rotation as opposed to a boost, then lambda to the lambda 1/2 is going to be Hermitian. Okay. Or sorry, unitary. So for a rotation, lambda to the 1/2 is unitary. On the other hand, S0I is the generator of boosts. And this is not Hermitian. In particular, S0I dagger is minus S0I rather than plus S0I. So that means that for a boost, lambda to the 1/2 is not unitary. So psi dagger psi is not going to be a scalar. However, this problem contains within it the seeds of its solution. In particular, what we can note is that Sij commutes with gamma 0 whereas S0I anti-commutes with gamma 0. Remember that gamma 0 is just the matrix 0, 1, 1, 0. So the statement that Sij commutes with gamma 0 is the statement that this entry up here is the same as that entry down there, whereas the statement that S0I anti-commutes with gamma 0 is the statement that this entry up here is minus that entry up there. So when you anti-commute S0I with gamma 0, you pick up an overall minus sign. Okay. So let's define the following object. So if psi is a 4-component spinner, let's let psi bar be psi dagger times gamma 0. So this is just a definition. Then how does this transform under a Lorentz transformation? Well, psi bar goes to psi dagger times lambda to the 1/2 dagger gamma 0. And, well, let's imagine now that we have two different cases. Let's first think about the case where lambda to the 1/2 describes a rotation. So rotation operators are unitary, and they commute with gamma 0. Okay. So in the case of rotation, that's psi dagger gamma 0 times lambda to the 1/2 inverse. But now think about the case where we have a boost. Boosts are not Hermitian because that S0I picks up a minus sign when you do a dagger. But every time you pass an S0I through a gamma 0, you pick up a minus sign because it anti-commutes. So in fact, the exact same equation here is also true when you have a boost. So that means that under a Lorentz transformation, psi bar transforms in exactly the way that you need in order to form a scalar. So in particular, psi bar psi will be a scalar under a Lorentz transformation. Are there any questions on that? If that was too fast, I encourage you to go through it again, just to convince yourselves. These sorts of manipulations, you know, maybe just one word of advice about these manipulations that we're going to be doing. You know, if you're ever not convinced about something, you can always just write the gamma matrices out explicitly. You know, there's 4 4x4 matrices. You can just write it all out and just check that everything transforms the way that I claimed. But you'll notice that in this proof, I never used the explicit form of the gamma matrices. I only ever used the Clifford algebra. I only ever used the fact, you know, the commutation and anti-commutation relations of the gammas. So very often, and you'll discover this probably in the next week or two, all of these computations involving spinors tend to be much easier to do if instead of writing gamma matrices out, you just try and use the Clifford algebra as cleverly as you possibly can. Good. So if we want to construct an action, we can begin by thinking of quantities like psi bar psi. So for example, what would happen if you just had psi bar psi in your action? Well, if you varied that with respect to psi, you would get something linear in psi. So if you want a derivative, then you need to construct a action involving a first derivative of psi. And because gamma transforms as a vector, you can easily convince yourselves that this is really the only scalar quantity that one can write down. And indeed, this is the Lagrangian promised for a spin 1/2 Dirac field. To verify that this quantity, that the Euler-Lagrange equations give you the Dirac equation, the easiest way to do this is to, just as when we were considering a complex scalar field, view psi and psi bar as independent variables and write down the equation that you get by varying with respect to psi bar. And what do you get? Well, you just get this operator, the Dirac operator, acting on that guy is equal to 0. It's the Dirac equation. Hopefully you remember that in your exercise where you studied the scalar field, it really makes most sense to think of phi and phi bar, or phi and phi star in that case, as independent variables. And you have an equation of motion for each of them. In this case here, we can also think of psi and psi bar as independent variables and write down the equations following from the variation of psi and psi bar independently. If you're not happy with that, you could just write everything out in terms of its real and imaginary parts, okay? And then you would get the exact same equation of motion. Are there any questions on that? So, let me make one comment about this theory, which I think is now apparent that I've written down the Lagrangian for a Dirac field, which is that this theory has a symmetry. What is the symmetry? Well, it's the symmetry where psi goes to e to the I alpha psi. So you multiply psi by some phase. And psi bar, remember, involves the Hermitian conjugate. So psi bar will get rotated by the opposite phase. And you can see that because the Lagrangian depends on psi bar times psi, it will be invariant under this symmetry transformation. In the case of a complex scalar field, we computed a conserved current using a Noether procedure. And similarly, one can use a Noether procedure to write down a conserved current. Can anyone guess what that current is? So one thing we know is that it has to be a vector, and it can't have any spinor indices. It just has to be a vector. Can anyone think of a quantity that we could construct using objects that we have learned about today that transforms as a vector? So, in the scalar theory that you worked out, what was J mu? It was phi star d mu phi minus d mu phi star phi up to some factor of I if you want to make it real. So similarly, we should look for a quantity that is built out of psi bar and psi that transforms as a vector. Any guesses? Yes.
Can't we just reuse the same current, but just replace a phi with
You could, but that actually turns out not to be the Noether current. That comes from this phase rotation. In particular, remember that the derivation of the Noether current followed from the variation of the Lagrangian with respect to its symmetry. The Lagrangian of the scalar field was quadratic in derivatives, and so you ended up with a current that was linear in derivatives. Here we're studying a theory whose Lagrangian is linear in derivatives, so the current is going to have no derivatives whatsoever. So your guess was very good, but can anyone tell me a quantity that transforms as a vector that has no derivatives and that is quadratic in psi? And those of you who took this class last year are not allowed to answer. Anyone? So remember that gamma mu Its claim to fame is that it transforms as a vector, but it is a matrix as well. So gamma mu by itself has, is a 4 by 4 matrix. And if you want to construct a scalar out of a 4 by 4 matrix, well, you sandwich it between a column vector and a row vector. And indeed, this guy is a 4 vector, and it transforms, and it is the conserved current associated with this symmetry. So, just as for a complex scalar field, the symmetry was associated with the fact that the particles that you get when you quantize the complex scalar field will carry a charge. The particles that we get when we quantize a Dirac spinner will carry a charge. And in particular, they will be positrons and electrons, which will carry the particles that are created by when we quantize this spinner field will be positrons and electrons. And this quantity that we've written here is the charge and current density associated with this electron field psi. And when we quantize the theory, this will turn into some collection of raising and lowering operators, which will measure the charge of some configuration of positrons and electrons. So one of the interesting things, the nice things to note, is that we sort of got for free that psi was a complex object. It was a complex field rather than a real field. That came along for free, and so it's very natural then to construct a theory of charged particles out of these spinners. If you want to construct a theory of uncharged spin 1/2 particles, then you need to find some way of setting psi to be real. One of the things you might ask is, well, why can't I just take psi to be a set of 4 real numbers rather than a set of 4 complex numbers? But the problem really is that these gamma matrices are also complex, right? They involve these Pauli matrices, some of which are complex. So that means that in general, it's kind of difficult to construct a theory of spin 1/2 particles that don't carry charge, i.e. real spin 1/2 particles. It turns out that it is possible, however, but one needs to impose an extra condition on your spinner field to get what are known as Majorana spinners rather than Dirac spinners. So neutrinos being the prime example in elementary particle physics of spin 1/2 particles that don't carry charge, they're described by Majorana spinners rather than Dirac spinners. Good. Okay. Any questions before I continue? I can't quite tell. Is this straightforward and relatively easy to understand, or are you guys having trouble wrapping your heads around this? So feel free to interrupt me and ask questions if something is unclear. So, having discussed the Dirac equation, let's now try and understand its solutions. Yes, question.
I just have one question for when we defined psi bar,
Mhm.
and we showed how it transformed. Is it only true for rotations or for boosts too?
It's true for boosts as well, right? I mean, yeah, it's sort of easy to show. No, that's a great question. So it's easy to show for rotations. So for rotations, how did we prove it? We used the fact that the Sij's were Hermitian and commuted with gamma 0. Okay. But for boosts, you use the fact that the S0i's are anti-Hermitian. Okay. So they pick up a minus sign when you do that daggering, when you do the Hermitian conjugate. But they anti-commute with a gamma 0. So every time you pull an S0i through a gamma 0, you get another minus sign that got rid of that first minus sign. Okay. So this is true for both boosts and rotations. Important question. Thank you for asking. Any other questions? Okay. So let's study these in a bit, the Dirac equation in a bit more detail. The first thing I do, so by the end of class today, we'll start writing down the solutions to the Dirac equation in more detail. But the first thing I want to do is write the Dirac equation a little bit more explicitly in 2x2 form. Remember those gamma matrices I wrote as 2x2 block diagonal matrices? Okay. So that means that if I took my 4-component spinner psi and wrote it as a set of two component spinners, one on top of another, then our Dirac equation will take a particularly simple form. So I'll give names to those two-component spinners. I'll call them psi left and psi right. So I've denoted them with subscripts L and R. And then the Dirac equation, so what was that? It was I gamma mu d mu minus m acting on psi. So let me write that out as a 2x2 matrix. Okay, so we get minus m's on the diagonal. And then remember that gamma mu, when we wrote it in this compact notation, was sigma mu d mu in the upper right and sigma bar mu d mu in the lower left. So you see that you just get a matrix differential equation, or a pair of differential equations for those two component spinners. And the interesting thing to notice, and the only reason why I point this out, is that if m is equal to 0, then these two equations that you get don't mix psi left and psi right. And so the equations just take the form sigma mu d mu of psi right is equal to 0, and sigma bar mu d mu of psi left is equal to 0. Okay, so that means that if we were interested in the specific case where m is equal to 0, you could actually write down nice relativistic wave equations for 2-component spinners rather than 4-component spinners. In particular, what this means is that for massless fields, when m is equal to 0, we can have nice relativistic wave equations involving only 2-component spinners, psi left and psi right. So in particular, you wouldn't need to consider both psi left and psi right. You could consider them each individually. And psi left and psi right are referred to as left and right-handed Weyl spinners. We met them in a somewhat more formal context when I was discussing the classification of the representations of the Lorentz group. We're not going to talk about them too much in this class because they don't appear very often in nature. Indeed, I think, as I mentioned, they were first discovered experimentally last year, okay, in the context of condensed matter systems, these so-called Weyl metals, okay, whose low-energy excitations are described by these massless Weyl spinners. But I only bring this up because I think it does help make clear. So the Weyl spinners are really sort of the closest in relativistic quantum theories to the non-relativistic 2-component spinners that you're used to dealing with in non-relativistic quantum mechanics. They're 2 components, and if you ask how they transform under rotations, well, they just get acted on by, you know, say one of those sigma k's right there. So they transform just like the 2-component spinners that you met in your non-relativistic quantum mechanics class. If you want to consider theories with mass, however, then you need to consider a Dirac spinner, which is to say a pair of Weyl spinners which are left and right-handed. in particular, the mass term that we wrote down above in the Lagrangian psi bar psi, if you wrote that out in terms of these Weyl spinors, what will that be? Well, remember that involved a gamma 0, and gamma 0 was the matrix 0, 1, 1, 0. So in terms of the Weyl spinors, that would be like psi left dagger psi right plus psi right dagger psi left, and that mixes the two component spinors. Okay, so enough mucking around with Weyl spinors. I would like to, in just the last few minutes I have, begin discussing the solutions of the Dirac equation. So, the first thing to note about the Dirac equation is that, remember, every component of the Dirac equation satisfied the Klein-Gordon equation. So that means that you can always find solutions that are of the form of some constant spinor u of p times e to the minus p dot x. Or, if I want to say that slightly differently, one natural set of solutions of the Dirac equation to look for are plane waves. And because each component of the Dirac equation solves the Klein-Gordon equation, the plane waves that you get will be labeled by a spatial momentum p, and the components of the Dirac field psi will go like e to the ipx, where p here is the 4 vector, whose 0th component is the square root of p squared plus m squared, and whose other 3 components are the vector p. So, just because every solution of the Dirac equation obeys the Klein-Gordon equation, we expect plane wave solutions of this form. Now here, u of p is some 4-component spinor, which is now a function of the momentum 4 vector p, really a function of the 3 momentum p vector. And the form of u will be determined by the Dirac equation. So what does the Dirac equation look like? Well, u is a function of p, not of x. So when you act with d by dx mu, that brings down a factor of minus ip. So the Dirac equation then just says that gamma mu p mu minus m acting on the 4-component spinor u is equal to 0. So this is a 4 by 4 matrix acting on some 4-component vector u, and it has to be equal to 0. To put it another way, we're looking for the 0 eigenvectors of that 4-component 4 by 4 matrix. So before writing down the solutions in full generality, which I suppose I'll have to do next class, let's just look at the theory in its rest frame. So let's imagine a particle at rest. Okay. What does that mean? That means that the 3 momentum p vector is equal to 0. And then what does that equation look like? Well, that equation is gamma mu, so gamma mu p mu minus m. What is that? Well, you can just pull out an overall m, and you get minus 1s on the diagonal from this minus m here, and you get a gamma 0, which is proportional to 1s on the off-diagonal element. So the solutions say that U, so the solutions in the rest frame are just 4-component spinners, which, if you write them as a 2-component spinner on top of a 2-component spinner, have those 2-component spinners equal to one another. So we conventionally introduce a normalization factor out there. That's just some convention. But the point is that if you take some arbitrary 2-component spinner and you take the 4-component spinner zeta on top of zeta, you act on it with this matrix, and then you get 0. So what does that teach us? That teaches us that there is a 2-parameter family of solutions for each momentum p mu. In particular, you could take your favorite basis of, so in particular, there's one solution for each choice of this 2-component spinner psi. So, for example, you could choose some nice basis. So, for example, you could let psi be some number, I guess we would call it psi up, times 1, 0, plus another number, which you might call psi down, times the vector 0, 1. And then an arbitrary solution of our Dirac equation will be some linear combination of these two, at least in the rest frame. So, said a little bit more physically, we're looking at solutions of the Dirac equation describing a particle at rest. And what we're finding is that there are 2 different solutions. Okay. One, which is proportional, where psi is proportional to that guy, and the other where psi is proportional to that guy. What is the name that we would give these 2 solutions? Well, remember that the rotation generator acts as a 2x2 diagonal matrix with the usual Pauli matrices. And a 2-component spinner with components 1, 0 is something that you would usually call a particle with a spin up in the z direction. And the one with components 0, 1 is what you would call a particle with spin down in the z direction. So, for example, this solution here would describe a particle at rest with spin up in the z direction, so spin pointing in the z hat direction. And this would be a particle at rest with spin down, so with minus h bar over 2 spin in the z direction. So, of course, I've just chosen a convenient basis where I've taken the 2 spinners 1, 0 and 0, 1, which are the eigenstates, the eigenvectors of sigma 3, the 3rd Pauli matrix. I could also take eigenvectors of sigma x or sigma y if I wanted to describe particles which have spin pointing in the x direction or the y direction. And of course, I've written everything in the rest frame, and the general solution, well, one way one could find a general solution is just by going back and solving the Dirac equation not in the rest frame. Another way you could find a general solution would be to take the solutions that I've written here and just apply a Lorentz boost. Okay? Remember that you can always, if you have a particle with mass, you can always go to its rest frame by a Lorentz transformation. So if you wanted to, you could find a general solution by acting on that vector there by some Lorentz transformation. Namely, the one that takes you from the rest frame to whatever momentum you're interested in. If you look in your textbook, I think that's probably how he does it. I'm not sure. I'll probably, next class, just go ahead and work it out explicitly. So let me just stop here, but before I do, let me see if there are any questions. So just to summarize, what we have here is we have plane wave solutions to the Dirac equation, just like there were to a scalar field or electromagnetism. But there's additional pieces of data that go along with these solutions. So just as if you were discussing the plane wave solutions of electromagnetism, you would have to specify the polarization of the electromagnetic wave. So there's two different polarizations of an electromagnetic wave, both of which behave like plane waves. And here, instead of a polarization, we have essentially a choice, a two-parameter choice, that describe what are known as the two helicities of a particle with spin. So that's something that we'll introduce in a little bit more detail next class. Any questions? Good. Okay, I will see you on Thursday.